Hi, everyone. Uh, Thank you for the introduction. My name is Vindhya Kuchibhotla, and I will be presenting on the low-powered embedded fisheye camera for deep computer vision. This is in fulfillment for my senior design requirement through the College of Engineering, and I worked under Professors Conrad, Little, and Escher in the BU ECE department. I was also on a team of 4. So how would you approach the issue of counting people in a room? Traditionally, this is accounted for through multiple surveillance cameras and a powerful computing server with all of the information and data. However, this is inefficient in deployment and in energy use. So my project is focused on coming up with an alternative for this problem, a device that my team calls Snell Lens, referring to the fisheye camera that we are using. So understanding how many people are in a room or in a building is important for minimizing energy waste, for emergency response, and for optimizing room usage. For example, knowing that only 3 people are occupying a room meant for 20 means that we can optimize the HVAC controls and the lighting controls for both an ambient temperature for everyone and for energy conservation. In addition, suppose we have an evacuation due to a fire. Knowing where people are located in a building and how many people is really tremendous for first responders to use. So essentially, the Snell Lens is a low-powered system that has capabilities consisting of an embedded processor and a fisheye camera to detect and count people in a room. This is to be used in large rooms like conference rooms or classrooms, hopefully with minimal obstructions in the view, and is to be connected to these HVAC systems or lighting controls. The competition for this product, so one can say it's like the Nest, where machine learning is used to control the temperature in buildings and rooms. However, that's not the extent of capabilities that we need. And typical motion sensor, however, that doesn't determine the number of people. In addition, we do have surveillance cameras, but as mentioned before, we would need multiple surveillance cameras, and there's a lot of image data that is transmitted. So just a timeline of the project. All deliverables were determined by the course itself. So it started in late September when we defined our project and the requirements necessary based on client meetings. By mid-November, we had our first prototype testing and demonstration, and late February was our second prototype testing and demonstration. We had just finished up a critical design review and evaluated the priorities we want to focus on for creating our final prototype, and unfortunately we had to stop our project. So I'll be going over the overall system first. So this is a block diagram of all of our requirements that are to be met according to our client. Please don't feel overwhelmed to read through all of it. I will be going over this. So essentially the device starts at the graphical user interface. Here, the user can set up how they want the system to run, essentially setting the parameters for the algorithm. For example, how much of a confidence level of a human do we want in order to detect them? And the operating state. So how long do we want to wait between movement to check again if there is anything going on in the room? Furthermore, this device configuration includes configuring the camera. So the camera has to have daylight and nightlight capabilities. So we need to focus on whether we want to enable the extra lighting or disable the filter for the optimal view from the camera. So this information is sent via a secure protocol to the processor. And the processor has both the algorithm running and the peripherals ideally. The peripherals are the camera and the passive infrared motion sensor, and the algorithm then runs on the image taken by the camera, and this information is then sent back to the graphical user interface, where we can hopefully see some historical data in the overall power consumption and count. So this is an abstraction of our second prototype. Here, we are running the algorithm on a computer, which is actually not one of our client's requirements. And this is actually the biggest challenge of our project because deep learning algorithms are not typically run on embedded processors such as the Raspberry Pi 4, and this is something that we worked on for our next prototype. So our expected prototype would have been using the NVIDIA Jetson Nano as the processor that runs our algorithm. So actually it is successful in running our algorithm and is capable of doing this in under 2 seconds, versus the Raspberry Pi 4 had difficulty hosting this. Fortunately, though, the hardware that we had for the Raspberry Pi is not compatible with the NVIDIA Jetson. So it's not ideal that we had 2 different processors running, especially for a low-powered system. However, this is the best way that we could have retained all of the progress that we've made. So now I'm going over the components and functionality. My responsibility on the project was more on the hardware design choices. So this is what I'm going to be focusing on in terms of integration. So essentially, the device is in standby mode when there's no movement. When there is movement, the passive infrared motion sensor is triggered. Imagine a cone that is spread out by 6 meters down the middle, and with 100 movement detected. The camera captures an image based on the parameters set in device configuration. So with a company mix, we put camera to all of our requirements, including the field of view, which is actually more than the traditional fisheye view, and having a photoresistor to detect if it's whether nighttime or daytime to help automatically set some parameters that can then be changed. So once the image is captured and saved, it is sent to the desktop via secure copy over using a network switch. So this is a secure protocol, pre-authenticated, and uses a secure shell. So even though I didn't work too much on the algorithm, I wanted to touch upon this. So YOLO, or You Only Look Once, is an algorithm that is publicly available and is for typical real-time object detection. So using bounding boxes, it determines the type of objects in a picture and has classes like dog, bicycle, car, for example, based on the processing in the neural network. So this algorithm that we're using is actually our client's research-based algorithm, and is specifically on fisheye images with an overhead view, only for the class of humans. So that is the change that was made, and we are trying to adapt this algorithm. So it starts with creating the neural network, and if the image is sent, then it runs the algorithm, deletes the image because we shouldn't be sending the image data in general, but because of the prototype setup we had, we are, which is why we're trying to delete the image, and then we display the count and repeat. So an important requirement is also having an enclosure for our device. So here is our product. The photoresistor is kind of sticking out here, and this is the camera lens, the IR LEDs, and the passive infrared motion sensor. So we wanted to build an attractive, robust structure for this in order for it to be successfully mountable. So we bought an extra large case here that provides all of the ports we need access to, but then the top is screwed on, which is great for modifying it ourselves. So we used an acrylic top and designed this to account for the hardware, like the PIR sensor here and the camera. So it's great for heat dissipation and for mounting. So I wish I could have a video demonstration for you, but instead I have pictures. So on the right, there's an image of the daytime view from the camera, and this is the nighttime view with the IR LEDs, which makes the image more pink tinted. And this is running on an image that we just fed into it. So the numbers here are the confidence intervals of the bounding boxes on the humans themselves. And this is how the algorithm runs. It is Python-based using PyTorch. So ideally, this count of 39 people would be sent to our full user interface, but currently it was just running on the machine. So we still have a lot of further work in testing. Like I mentioned, the actual user interface needs to be developed, and just setting these parameters, because we're doing this manually as of now, but we want any user to be able to do this themselves. Furthermore, we want to make sure that the system is robust. It is currently mountable with just the Raspberry Pi. However, we do have that additional processor now. And we also need to just check the algorithm performance, testing this in an overnight setting in the typical room that we'd like, and really gathering that information for like power consumption analysis and generally how it performs. I want to thank my advisors for this project, the course instructors, and everyone who helped me in this process. Thank you.